And feel free to ask questions. The recordings are all very informal, okay? So this is problem 2.8. It's on page 27. A disabled automobile is pulled by means of two ropes as shown. So there's a figure off to the right if you want to look at it. The tension in rope AB is 2.2 kilonewtons and the angle alpha is 25 degrees. Now, of course, the angle of AB is 30 degrees. And if you don't have your book, you might look on with your device. I've posted the chapter. Let's see. Knowing that the resultant of the two forces applied at A is directed along the axis of the automobile, determined by trigonometry: A, the tension in rope AC, B, the magnitude of the resultant of the two forces applied at A. So let me sketch it on the board so that you can see what we're looking at. So this is problem 2.8. Here's the car that is disabled and being pulled, I guess, by two ropes, whatever. Anyway, there is a 30-degree angle here, and they called this angle alpha, but then they told us that it equals 25 degrees. And this is 2.2 kilonewtons, I believe. I'm doing this from memory. This is point A, point B, and point C. Let's see how much of that I got right. B, C, 30, yeah, 2.2. So what we're trying to find out is the tension in AC. And we're also trying to find out, what else? The magnitude of the resultant of the two forces that act at A. In other words, we know that when we add these two together, we're going to get a force that acts horizontally. The question is, what's that total magnitude? Okay. Do you see how this is simply a vector addition problem? In fact, if we did this graphically, what we would do is we would say, well, we know the line of action or the angle of AB, and so we'd simply draw a line in that direction at 30 degrees from the horizontal. Okay. That force acts along that line, and we know its magnitude. In other words, we could scale this to represent 2.2 kilonewtons. So its length would represent the magnitude of the force. Okay. We also know excuse me, the vector AC lies along a line 25 degrees off the horizontal. So let me sketch it here. So there's horizontal, there's 25 degrees. I don't know why I'm making my horizontals solid lines. I should probably switch that around. So we'll make the force vectors solid lines and the horizontal reference dotted lines. Now, if we know, there's something we know that's really important, the resultant, or in other words, the addition of these two vectors has to end up being a line that's horizontal. You see what's wrong with what I drew? They wouldn't add up to there. All I've done is I've taken, okay, so this is A, B, and this is A, C. I've taken the two vectors and put them one head to tail. It doesn't matter what order I do that in. Either one's fine. But I haven't drawn AC long enough, have I? Because we know that when we add the two vectors, we have to end up with a resultant, a sum of AB and AC that is horizontal. So do you see how the angles or the line of action of the two force vectors controls how long AC is once we've scaled AB appropriately? Okay. So hopefully that graphical argument makes some sense. Now let's do it with trigonometry. We have several tools at our disposal. What all did we have? Well, we had law of sines, law of cosines. Oh, what else did they tell us about? Parallelogram rule, triangle rules don't really help us a whole lot. We'd have to use either law of sines or cosines. I think probably, well, you probably remember that that's 25 degrees also, don't you? How do I know? Because they're opposite interior angles. Remember that? These two lines are parallel to one another. Well, let's just do everything we can. Let's find out this angle as well. It shouldn't be too difficult. You can tell me. It's a triangle. Sum of interior angles are?
180.
180. So all we got to do is take 30 and 25, which is 55. Take that away from 180. What do you get?
125.
25. I have to think for a second. 55, yeah, that's right. Good. So 125 degrees. Okay. So how could we find the length of this? Well, we don't know the length of this side, do we? AC, and we don't know the length of the sum of the two, which I will simply call AB plus AC. Okay. So, excuse me. I suppose we could, let's see, probably easiest is to use the law of sines. Because we know all the interior angles, A, B, and C. Now, unfortunately, they got A, B, and C. I would prefer alpha, beta, gamma. So if we did something like, we're already using A, B, and C. So if we call this angle alpha, this one beta, I suppose, and this one gamma, then the way I like to write the law of sines is sine of, and let me rename these, I'm sorry, I hate to do this, but I want to make this problem just a little bit more general. Okay, so sine of alpha divided by what? Well, it's the side that is opposite the angle, so it's this side. Let me call this side A. Let me call this side B and this side C, and you'll see why in just a second. So sine of alpha over A should be equal to sine of beta divided by the length of the opposite side B. Understand that lengths now are going to be forces. Okay? And then sine of gamma, this angle here, over C should make all of this true. Okay? So if I know the length of one side and the angle, for example, I know B and beta, excuse me, then I know what all these ratios are. Okay, go ahead.
On the PowerPoint, Q, R, and P, what did those
Which
stand
one's
for?
which?
For the, under the law of sines.
Right, so we're just looking at a triangle here is all we're really doing, okay? So you could apply this to any side you like. So Q, R, and P, if R is the resultant, let's just take this triangle for example, then B, the angle would be the angle in here, you see? So they're using A, B, and C as interior angles, and they're not really well in the slides.
Okay.
That's why I like alpha, beta, gamma, clearly.
Okay.
Go ahead.
What page is that problem on?
Oh, it's page 27. Yeah, no problem. Okay, so if what we want to know is the length of A, well, look, to get A, all we need is alpha. So we can take this equation and rearrange it. So let's see, sine of beta over B. Actually, we'll have to reverse it, won't we? So let's just write down A. The length A that we want is equal to, we'll just move this over here, sine of alpha over sine beta, but then we've got B multiplied in the numerator. So let's see, we need sine of alpha. Alpha is 30 degrees over sine of beta. Beta is 25 degrees multiplied by length B, and length B is 2.2 kilonewtons. So bring out your calculators, please, and just plug this into your calculator. Let's see what we get. Sine of 30 over sine of 25 times 2.2 kilonewtons comes out to what?
.60,
246?
2.60.
2.60. So this is 2.60 kilonewtons of force. Now, could we simply add 2.2 and 2.6 to get the resultant C? No, they don't lie along the same line. I want to convince you of something. To make the video a little long, but that's okay. I want to convince you that, let's see, 3 plus 4 equals 5. Do you believe me? It's like that video that made viral rounds, right? The 2 plus 2 is 5, remember that one? Okay, so 3 plus 4 is 5. You actually agree with this already. I know you don't think you do, but you do. In one case, if we add 3 units and, make this one longer, 5 units, like this, then actually you and I would agree that's 8. Which is the answer that you expected. But if you walk 3 paces north and then you walk 5 paces east, 1, 2, 3, 4, 5, you have gone a distance, 4, 7, that's what I meant to do. Got to be consistent here. There we go, 3, 4, 5. So if you walk 3 paces north, 4 paces east, you have moved a distance of 5 paces. 1, 2, 3, 4, 5, 6. I'm not doing too good today, am I? Try that one more time. So you agree with me that 3 plus 4 equals 5, right? You see how important direction is? Makes a big difference. In the same way, I can't just say that 2.2 plus 2.6 equals whatever C is supposed to be, right? 4.8. That C is not 4.8. C is less than that. If these two vectors were in line, then sure. But they're not in line. And so the sum of A, B, B, C in the original terminology, the sum of these two vectors, is less than 2.2 and 2.6. As a matter of fact, we could figure out their sum because, look, we could solve for C, couldn't we? In fact, we could have solved for C as soon as we knew 125 degrees. Our equation would look a whole lot like this. In fact, rather than modifying it, I'll just write it again. What do we know? Well, we know sine alpha A, sine gamma C. C is what we want. We know all the angles. So if we solve for C, then that's what would it be? Well, let's see. C, pull it over to the other side. Sine gamma over sine alpha times A. Except I don't really want to use A. I would rather use B and beta because that's what was given. Okay? So all I'm really doing is using this equation now. Okay? Just rearranging it. So let's try it. We'd have sine of gamma. Gamma is 125 degrees over sine of beta. Beta is 25 degrees. Length opposite B is 2.2 kilonewtons. So tell me the magnitude of the resultant C, or whatever you want to call it, AB plus BC, or AB plus AC.
.26.
4.26. Sounds good to me. That's less than 2.2 plus 2.6, isn't it? That'd be 4.8. Okay. That's the total force. Now wait a second. It doesn't seem right. How do you apply an effort of 2.2 kilonewtons and 2.6 kilonewtons and get less out of it? I'll tell you how. A component of each of these forces fought each other. You see that? As a matter of fact, these components are exactly the same. That's the reason that the sum of the forces ended up lying along the horizontal lines, because the horizontal, or the vertical, if you will, components of A, B, A, C canceled each other out perfectly. See that? Go ahead.
Just to reiterate, what exactly are we trying to find?
Well, let's see. We're trying to find the tension in rope AC. There it is. No, AC is this one. So that's this one, 2.6 kilonewtons. What else are we trying to find? The magnitude of the resultant of the two forces applied to A. Right there, 4.26 kilonewtons.
Okay.
How hard are we pulling the car forward?
Okay.
And by the way, will the two ropes break? The one is carrying 2.2 kilonewtons, the other one's carrying 2.6 kilonewtons.
Also, wouldn't the ropes be way more narrow?
Well, not according to this. Would it be wise to make the ropes more narrow?
Yeah.
It would be wise.
Making sense.
Why? Because we'd have lower force in the ropes.
Yeah,
Right?
there'd be less force, it'd be more concentrated, and like you said, the.
No,
forces-
less vertical force to
Yeah.
tend to break the rope. Worst case scenario would be to take the ropes and put them almost vertical and try to pull the car. There's going to be a ton of tension in the rope. But wait a second, don't we already do that? Don't we already load wire rope that way? Anybody think of an example where we load wire rope at extreme angles relative to the direction of the force? Well, I think it's getting windy outside, and you'll probably go to a stoplight at some point, and you will see a stoplight. Anybody ever see how big a stoplight really is?
Yeah.
They are not small. And you'll see it supported by two cables like this, where there is a large angle. What do we really want? We want a force, a resultant force that offsets the weight of the light, right? But what do? We pull really hard at an extreme angle.
So that it won't sway.
Well, that does keep it located horizontally, but it can still, of course, move around at the bottom of that. Also, it's not really convenient to have extremely tall poles, so we can have nice narrow angles. We need to span the road, right? But there are cases where it makes sense to put a lot of force in the cable so that we can get a relatively low force as a resultant. Okay. Any questions about all this? Well, let's beat the problem to death, shall we? We're not quite done. What about the law of cosines? Could we have used it? We already know the direction of C. We already know it has to be horizontal. And so, let's see, it looks like we'd have to say the resultant squared equals p squared plus q squared minus 2pq cos beta. Notice that to use this equation, let me jot it down over here on the board. To use that equation is a little more difficult because we really still need the law of sines. R squared equals p squared plus q squared minus 2pq cosine of the angle between p and q. So p and q, in our terminology, we've got a, b, and c. So let me switch this out. C squared equals a squared plus b squared minus 2ab cosine of the angle between a, b. So that would be angle gamma. So what all do we have and what all do we lack? Well, we have b. But notice we did not start the problem with a. And so we'd have an unknown there. We've got gamma, that was easy from the sum of the interior angles, but we don't know c, so we'd have one equation, two unknowns, you see. Sometimes it'll be more convenient to use the law of cosines, sometimes the law of sines. In this case, the law of sines was better. Why? Because we had the other angle. If we didn't have the other angle, if instead we had the other length, then the law of cosines would have been better because we would have had a, b, and so on. Okay? Of course, we'd have to still have gamma. We'd have to have this angle between a and b, or we'd be back to using the law of sines. Okay? Any questions?
You're saying better, does that mean you could use any of them to
Well,
solve it? or-
no, I don't think better. I think it's your only option. I was trying to be nice. Kind of forced to go one way or the other. Not exactly a choose your own adventure book. Any other questions about this problem? Did you get confused about what we were trying to find along the way and forget? That's okay, that's normal. One of the key things is to think about how the math and the geometry we're playing with relates back to the original problem. What were you gonna say?
So, like, I guess I'm just thinking out loud, like.
You're fine.
You can find AC just by, because that triangle is just the top portion of that original problem, right? It's just like expanded.
So you're saying you can find this
Like,
vector?
you were able to find that just by putting that side, the right side on that triangle, and that counts as that.
I see, yeah, all I did is I took AC and I moved it over so that it was at the head of AB.
Yeah, and you can just do that.
Yes, you can move. Now, some forces, their point of application makes a difference, especially when we start talking about the moment of a force. But the effect of a force on a body, as long as that body is small, it's a particle, it doesn't matter, right? Because the body doesn't have any size, so it's always at that same point. But yeah, we can move it around. Okay. Anything else? Okay.